Hello and welcome everyone. My name is Peter Robinson. This is your Ethereum Engineering Group meetup. And today it's me going to give a talk on random number generation and blockchains. So I'm the head of blockchain research at Immutable, looking at all sorts of things over the horizon of how we make the platform more secure, better, and working on what makes a game great. And part of that research has actually been looking at random numbers because some games do want to do stuff on chain. So let me share my slides. Okay. All right. So hopefully everyone can see my slides, and I'm going to set up so I can see the chat as well. Yep. Okay. So, all right. Can people see my slides?
Yes.
All right. Brilliant.
Yes.
Yes.
Okay. Cool. Okay, random number generation on an EVM-based blockchains and rollups. Yeah. So, quiz question for everyone as we start off. Prev ran DAOs there, so could you use this code in, if you were writing a game that has some sort of loot box, so one of these things where you open it up and you get a randomly selected set of stuff. And, so assume you send in 1 ETH and then you open up this random box. What is wrong with this code to, just do this sort of operation? So no takers. Okay. So imagine that code is called here. So we've got a contract called onEVM, and you've got your constructor where you've got that game contract, and then you go game, open the loot box, you send through your 1 ETH, and then you check the value that you've got out of the loot box. And if you don't like the value, then you revert. And so, yeah, it means that because you've just got this, where you're doing it all in one transaction, where you're getting your random number, and then someone can just be actually calling you from a different contract, then you're blown. And you might be thinking, oh, but maybe you could check that it's an EOA. Well, wallet contracts are really quite popular these days. And so wallet contracts invariably allow you to do a multi-call. So if you're allowing people to use, say, Passport or some other wallet, then they could easily call into your open loot box function and then have a separate thing where they check the amount that they've got, or the value they've got. So yeah, so trying to do the unwrapping of the random number, and so the request and the fulfillment all in one transaction is going to mean you as a game lose out to players who know what they're doing. So today I'm going to talk through just top level random number usage, and then I'm going to talk about how you go about producing random numbers, then walk through some lower level technicalities, talk about off-chain sources you can use and on-chain sources, and also talk about random sequences as well. So when we think about random numbers on chain, you've got two different types of usages in general. You've got, like, say, non-financial, non-deterministic events that you want to have happen. So in a game, for instance, you might have an NPC, so a non-player character, and they'll walk in a certain direction, say, and that direction might change randomly. So the random number generator for that probably shouldn't be on chain because it's a really low cost, low value thing that's occurring. Whereas maybe you've got a financial transaction or something that has high value, For instance, that you could have a randomly generated NFT with randomly generated attributes, or you could have a loot box, or I mean, to talk about, like gaming as in gambling, you can imagine you've got a poker game and you're going to draw the next card off the deck of cards. And so, again, that's something where there's probably going to be money involved. And so you might then decide, right, that's a good time to do it. But for low value events, you don't want to be doing them on chain, I think. And so if you've got this non-financial, non-deterministic event, this low value event, you should be using like your standard SDK, like Java or Golang or Rust, or maybe you've got using a game system. And so again, like you'd use your reality engine. Is that the one? Anyway, you use some sort of SDK, not on chain. And so for these financial non-deterministic events, so you do need secure random numbers, and so you can try to do them off-chain, or you can do them on-chain, or you can do them on-chain but using off-chain systems that are secure. And so I'm going to talk through the on-chain and off-chain systems that surface the numbers on-chain. So a two-step process is needed when you're generating random numbers. So the action has to happen to request the random number, and that has to happen in one transaction that happens in one block. And then at some later point in a different block, you're going to have a different transaction to fulfill the request from the first transaction and return the random number. And by splitting that out, you're not going to have that reversion problem. So yeah, so you need to separate it out so you don't have the game players revert, or the people consuming the random number. And you need to link the request with the response. So you can imagine you could have a system where you're putting in multiple requests, and you wouldn't want the game player, the consumer of those random numbers, to be able to cherry pick which random number they're going to use for what. So you need to say have each type of usage linked and the sequence of usage linked, so that one request gets a very specific response. And so if you've got a payment involved in the overall process, that needs to happen with the request, because otherwise what will happen is that the game player will request the random number be generated, but then when it comes to payment and consumption, they'll say, oh, well, that random number's not interesting, so they won't do the fulfillment. And so you need to do the payment with the request and then do the fulfillment. So let's drill into things a little bit, a few of the technicalities. Or actually, before I go further forward, is all of that, does all of that make sense? Okay.
Yes, it does.
All right. Cool. All right. So random seeds, a seed in random number talk is a value from which you generate other random values. And so the idea is that you normally the sources in blockchain systems can only generate one value per block. And so if you've got multiple applications, say multiple games, and you've got multiple players, and maybe multiple players might do multiple transactions all in the one block, then you can't just be using that one number for everything. So you've got to have a way of using that number as a seed and deriving other numbers from it. Yeah. And so what you can do is you can personalize the random number you've got, the seed you've got, to give a more personalized seed that the individual can use. And so how you can do that is you maybe could do a message digest of the address of, say, the game contract or the application contract. And then assuming message sender is a proxy for the game player or the consumer of the random number, then you combine that. And maybe there's a request ID, which is per user. And then you bring that all together with the seed and you hash that. And that'll give you a personalized seed so that for every game player, and for each usage, you'll get a different number, which is obviously what you want. Sometimes, though, you will decide that you need, say, multiple values. And so when you do that, you need to be very careful about how you do it, so you can't be manipulated. So you need to use a pseudo random function, a PRF. And so what you do is you have essentially the message digest of that personalized seed and an integer. And doing that will again generate an array of different numbers. And the thing to make sure, though, is that you need to lock those game players in when they do the request, so that they say, I'm going to need 5 numbers, or I'm going to need 3 numbers. So if there was some aspect of the game where it could be variable, of the number of the quantity of numbers you're going to need, then you need to lock them in at that request, because otherwise what you can imagine an attacking game player could do is they could run that PRF themselves and go, oh, the value 25 is going to be really good to me. So they could somehow rather try and consume values 0 to 24, doing, something of low consequence, and then use that value 25 as something that's important and maybe advantageous to them. So if they were locked in at the start, they would have to maybe be paying for all of those numbers and be, like locking in what they're going to do with each number. So yeah, locking them into exactly how many are going to be returned is important when you're going to return an array of numbers. So another technicality, another thing to consider. So in at the start of this call, actually, just before we clicked record, we were talking about generating random information and how you can do it. And David pointed out that a great way is shining a laser through a lava lamp, and how, that can give you some good bits. And then I said, that you've also got the idea that, you record the nanotime of a computer doing an event on in a system, say even in the cloud, and from the eyes of the attacker, that's hard. But you might say combine multiple of these low quality events that might only have a few bits of uncertainty in them to create this higher quality random number. And so that idea of combining many sources of random number in a normal cryptographic system generally yields a much higher quality random number. And that way, if, say, one of the sources is compromised, then, it's not a problem. So unfortunately, that concept of combining random sources doesn't work in blockchain. And the reason why it doesn't work is that you're in a deterministic environment where you're combining, say, a random value with a value that might be able to be manipulated, and the point at which the manipulation can happen is after the pure random value has entered the system. So hence, if you do combine, say, some system that is potentially compromisable on chain with some high quality off chain random, then you risk essentially watering down the goodness of the off chain random. So yeah, you've got to be aware of combining sources. Another thing to consider is the delay between requesting and fulfillment. And this is particularly important for on-chain sources. So there must be some sort of delay between when a game requests a number or a seed value and when it's fulfilled. And the real question is, how long is long enough? And so, you could say, all right, we're going to wait until the value is final. And so, you put your request in, it's been finalized, and then you come up with the response. So in that way, like locking in the actual request and being sure it's not going to revert. But what about systems that have got single block finality? Can you that very next block grab the random number? And so how I think you can think of this is that typically the current block is when you've requested the number. And then, the next block, typically if you're using prevRandAO or block hash, it's based on the previous block. So hence block plus one is going to be referring to the block that the user is putting their transaction into. So that I think would be a bad idea. And so then block plus two then is the block that you're wanting to, have as the hash. And so then really it means that by the time you're at current block plus three, that's when you could actually be doing your fulfillment. And so having a delay tries to ensure that game players who are savvy can't in some way influence the situation or help to guess the value. So, before I go on, does anyone have any questions?
Yeah, I was just typing one, Peter. So am I correct to understand that if you submit a transaction and the block that contains that transaction is rejected, and you need to resubmit the transaction, you'd want to change your random numbers that were used in that transaction,
Ah, yeah.
depending
So,
on how they're calculated, right?
yeah. So assuming that you're submitting a value, and so you're assuming that you get to come up with a random request ID. So typically you could just use sequential request IDs, because I think that or depending on how you design your system, it shouldn't be influenceable. So if it's an off-chain system, as we're going to see, there are two types, and generally, if you use VRFs, you're not going to be able to influence the value. But no, I think it's going to come down to the design of the system, but typically I think you aren't going to have to worry about that. But it does mean you are right that as soon as if you were, say, putting a random number into a blockchain system, as soon as that random number hits the mempool, then everyone or all the savvy people are going to be able to see it. And so your system then has to be designed such that even non-savvy players are not disadvantaged. And so, yes, you'd have to be conscious of that when things hit the mempool, that you'll be able to see what's going on. So, and are there any other? Did that make sense, David?
Yes, thank you.
All right, cool. I don't think there are other questions. So, let's dive into on-chain sources. So the block hash of a block is the hash of everything in the block except for the extra data field. So you can think of this as a fingerprint of the entire transaction history, the whole blockchain history up to that point. And so in Solidity, you can call down into an opcode, and essentially you call block hash, and then you pass in a block number. And that block number can be any block that's been in the past 256 blocks, but it can't be that block itself because it's referring to the block hash of a previous block. So that's one number that you could do. And the issue with that system is that you could have a block producer and they could calculate what the block hash was going to be. And then they could put a transaction in of their own, and they could like have a number, like they could have a 32-bit field or a 256-bit field that they could manipulate, and they could calculate many, many, many candidate blocks with candidate block hashes and thus manipulate the block hash. And so that's certainly possible to do. Another issue is that you could imagine that, say, if you've got a quiet chain, so a chain that doesn't have many transactions, and with Ethereum, that's never going to happen. And with even most L2s, I don't think it's going to happen. But with the rise of app chains, L3s, I think there is the possibility where you'll have chains where they might have, like, say, 10 minutes in a row where there are no blocks on the chain, no transactions on the chain. And so, you can imagine if you've got a perfectly quiet chain and maybe there's just a single block producer, and, so maybe there's no information going in that's random at all, then an attacker could potentially calculate, if they put their transaction in at this block, what the calculated block hash will be. And so, that could be a thing. And so even people using your chain could be able to guess the right value. So that only would work, though, if you were putting a transaction in and there weren't transactions coming in from other people. Another methodology is to use Prev-RANDAL. So this used to be called difficulty. And so the Prev-RANDAL is the output of the RANDAL for the previous block. And so from the Shanghai hard fork onwards, like the opcode's been renamed and RANDAL's calculated typically using this sort of formula where you do the hash of the previous RANDAL figure value, and then the BLS signature of RANDAL combined with the chain ID and the block number. And so the thing to think about this equation is that, so RANDAL's constant, the chain ID for a certain chain is going to be constant, and then that block number is going to, is not an influenceable value. So the block producer isn't going to be able to, say, insert new transactions or do whatever they like to influence this number. It'll be uninfluenceable. So different thing to recall, though, is that different chains may have slightly different formula for this. And it will come down to the particular chain as to exactly how they do this. Yeah. Oh, and note the use of BLS signatures. So BLS signatures don't contain a value that the signer puts in. So ECDSA uses a random value, but obviously that random value could be manipulatable by the signer. So hence the use of BLS and not ECDSA. So there is a potential issue with the use of Prev-RANDAL that you need to be thinking about. And so, you do that transaction one where we lock in the block number that we're going to get Prev-RANDAL for. And so, yeah, in fact, that's actually something to actually emphasize, is that, so when you do this transaction to request the random number, you're going to say, I want Prev-RANDAL or block hash, but I want Prev-RANDAL to be gathered for a very specific block. And the reason why you do that is that if you just say, I want Prev-RANDAL, then the user is going to do the fulfillment and they'll be able to have a look at the number and not be happy with the number and then wait in the next block or the block after. So So you've got to be able to say, I want it for this very specific block. But the problem with Prevran DAO is that you can't, it will only give you Prevran DAO for the previous block and not a range of blocks. So it means that if you're, you've got to somehow or other get a transaction to go in at just the right block number. And if you don't, then the Prevran DAO that you were trying to get value won't be available to you because you'll be on the wrong block. And so the only way that I can think of that you can sort out this complexity of having to get your fulfillment in on just the right block is to have a transaction that the block producer puts in each block to record the value of Prevran DAO. So essentially, you then create an array from 0 block number of the Prevran DAO values that have been created for the blockchain, which is not an ideal way of doing this, but it's the only way I can think of, because otherwise you're guaranteed that the system won't be resilient because you'll be trying to get the Prevran DAO for a certain block number and you'll miss getting the transaction into the correct block. Another consideration with Prevran DAO is that, so the block producer is going to know the value ahead of time. And this probably won't be important, but it does mean that the block producer will know stuff a little bit ahead of everyone else, because what they'll see is at block number n, the RANDAO figure value for the previous block producer for block n will have been created. And so they know what their private key is. And so they can calculate what the RANDAO will be for the block that they're producing, block number n+1. And so everyone else only gets to find out about the Prevran DAO for block n+2 when block n+1 is produced. So the block producer for n+1 knows about the value one block earlier, and that isn't a big thing, but it's still something to at least acknowledge. Another part of this whole scenario and something to consider is that rollups sometimes need a completely deterministic environment. And for instance, Arbitrum always sets the block hash and Prevran DAO to 0. So if you're going to rely on using them, then it's just not going to work on Arbitrum and some of the other rollup systems. So secure random on-chain is either very hard or impossible. And so having to design your blockchain so your block producers always put a transaction in to capture the Prevran DAO is going to be pretty hard. And if you're on a system like Arbitrum where the Prevran DAO and block hash just aren't available, then it's impossible. So at that point, you need to turn to off-chain sources. And before I dive into that, are there any questions about on-chain sources? Okay. So off-chain sources, there's a concept called verifiable random functions. And so a VRF is an algorithm where you have a asymmetric key pair, private key and a public key. And the idea is that you give it an ID, a request number, and you then the system combines the request number and the private key to produce a blob. And you can use that the public key to verify that the output is a result of the input. And so, so private keys combined with the input value alpha produce a value beta, And then the public key combined with the input value alpha can be used to verify that beta was generated using the private key according to the algorithm. So some very smart cookies came up with this algorithm, and I think it's awesome because, and this system, so this is a image from Chainlink. You can imagine you've got your smart contract, it comes up with an ID number, and then Chainlink's off-chain system with its private key, it generates the pseudo-random number. The VRF then on-chain has a contract which verifies using the public key that the value is created correctly. And then the random number is passed to that smart contract back at number one. And yeah, so it's a great little system. And so Chainlink have got a system where they've got a single private key, and it can fail over between geo-dispersed servers. And so I guess the big trust assumption there is that Chainlink's private key is never released, never leaked. Supra, previously Supra Oracles, they use an MPC methodology where they've got several servers that cooperate to generate a random value. And so I guess you're trusting that the multiple private shares aren't somehow or other leaked. Also, the performance of the Supra isn't as good as Chainlink. So Chainlink, the verification is simpler, whereas Supra, you're having to use BLS. And so it's more complicated, so it uses more gas to do the verification. There are also systems called quantum random number generators, so QRNGs. And so the idea is that the server assigns a random value, and that then on chain you verify the public key, and then you say, oh, yeah, I accept this random value. And there's a few things that I have concerns about with this sort of system. So there's no way to prove that a certain random value is fulfilling a certain random request, I think, or it's hard. So maybe the request could be signed along with the random value or something like that. And also, how is there a failover situation? So if there is, how do you get to understand if you're getting the right trusted value or not? So anyway, the ANU's got a QRNG, and so it's probably worth investigating further. But to me, I do have concerns. I think for me, I can understand the VRF methodology and the idea of it creating a number. And I think you got to think that in the eyes of the attacker, these random numbers are going to be equal, even though one's got using quantum effects. The just having a PRNG that you cannot observe and you can verify is generated using a request ID that you've given is pretty powerful all by itself. Are there any questions about the VRF design or QRNG? Okay, so random sequences. So I did say that you'd have to do one request and then do fulfillment in a different transaction. But you can use random sequences to do one random number per transaction. And so you combine the request for the next random with the fulfillment for the previous random. And I guess the question that you've got to scratch your chin about and have a think about is, well, what could go wrong with this? And so savvy players, will know ahead of time what random number was generated. So they're going to be able to have a look and work out what number was generated, and then be able to think, well, when in, say, an hour's time, I consume that random number, this is the number it's going to be. So that might have negative consequences. So a way of getting around this is that you need to have a set of sequences. So maybe you've got, say, 5 usages of random numbers. So each usage has to have a separate sequence, so that I can't, say, use the next random for low value usage A, and then use like the one, say, in three random numbers time in the sequence for usage B, which is high value. You also can't use this sort of system in a shared activity. So if you did, then you can imagine that more savvy players may be able to see the random number ahead of time, whereas your less technical players won't, and that would be unfair. So, random numbers. My final thoughts is that it's actually not too hard to generate a number that looks randomish on chain. You know, you could do a kickhack 256 of the block number and it will look random, but it's really very difficult to generate numbers that aren't susceptible to calculation or guessing within the constrained environment of the EVM. And, you know, assuming you've got sufficiently savvy game players. And so if you're going to be, you know, like dealing with tens of thousands, hundreds of thousands, millions, billions of dollars, then people will be motivated to try and beat the system. So, yeah, you've got to try and design your system so that it, you know, can handle that. The merch store is still open and running. Future talks. So in 2 weeks' time, we've got Andreas, who's going to talk about L2 transaction fee API standardization. We've got Lecky, who's going to talk about Uniswap v4 and the incubation program that he participated in. And then a little bit later, we've got David, who's going to talk about how AI is going to assist Web3 adoption. If you're here today, you can watch the YouTube videos of or recordings of the talks. There's a Slack workspace you can join. Yeah, if you're watching the YouTube video, you can join live and ask tricky questions. Sometimes there are code examples, in which case they'll end up in that repo. And are there any questions?
Great job, Peter. Thank you.
Yeah, looks like no questions, which is all good as well. Yeah, I think the answer of random numbers is it's pretty hard, isn't it? It would be good if it was straightforward. But yeah. Anyway, have a great day, evening, night, everyone. And I will talk to you all in 2 weeks' time.
Thanks, Peter. Goodbye.
Bye-bye.